We will do the acceleration analysis of 4-bar pin jointed mechanism using analytical method. So you can see a 4-bar pin jointed mechanism which has a 1 degree of freedom and it is in the motion. So we will do its kinematic analysis, and kinematic analysis involves first of all the position analysis of the mechanism, then the velocity analysis, then acceleration analysis. So first step before doing the acceleration analysis is that the synthesis of the mechanism should be complete, which means that whatever the required motion was for that mechanism, the mechanism has its 4 lengths known. So these 4 lengths, if you see the figure here, this is the link number 2, one length, and this is the link number 3, the second length, this is link number 4th, the third length, and this is the link number 1, which is the ground. So these are the 4 lengths which are required when you are drawing a 4-bar mechanism, and we will call these lengths as A, B, C, D, which are shown here. So D is the length of link number 1, A is the length of link number 2, B is the length of link number 3, and C is the length of link number 4, because we always number the start the numbering of the mechanism from ground, which is D link. If the synthesis of the mechanism is done and we know that these are the 4 lengths of the mechanism for the 4 bars, then the next step is to do the position analysis. For the position analysis, we make a global coordinate system. So here is the x-axis global and this is the y-axis global, and in this xy coordinate system we have put this mechanism in a way that the link number 1 is along x-axis, which means that its angle with respect to x-axis is 0. So theta 1 is 0. We put the second link at a given theta 2. So this theta 2 is provided by us, is provided by the user, and based on this theta 2, this mechanism must have an unknown theta 3 and theta 4. So we solve for theta 3 and theta 4 in the position analysis. So an equation is developed. So for a given theta 2, you can find the theta 3 and theta 4. So this is your position analysis. Okay, after the position analysis done, you have to move towards the velocity analysis, and in the velocity analysis what you do is that you find out that A is the point where link number 2 and 3 is joining, B is the point where link number 3 and 4 is joining, O2 is the point where ground link and link number 2 is joining, and O4 is the point where ground link and link number 4 is joining. So based on this, you give one velocity, angular velocity, to an input link. That is link number 2 for us. So we give an input angular velocity to this. So this angular velocity is given. This is in this case clockwise, and we are taking clockwise as negative. So for this omega 2 angular velocity given to link number 2, if we have to find the angular velocity of link number 3 and link number 4, that will be known as the velocity analysis. So when we find the velocity of link number 3, it is known to be omega 3, and when we find the angular velocity of link number 4, it is omega 4. We are not only interested in the angular velocity, but we also are interested in the linear velocity. So that's why we find the linear velocity of point A, and we also find the linear velocity of point B, and we also find the linear velocity of B point with respect to A point. So these velocities are also important. When we are able to find these velocities, we can find velocity of any point of the mechanism, whether it is on link number 2 or it is on link number 3 or it is on link number 4. So when the position, velocity and acceleration analysis is done, we are ready to do its acceleration analysis. So for acceleration analysis, it is essential that position and velocity analysis is already done. And we also have mentioned a point C here. Point C means that this is point C is additional point somewhere on the coupler. So it's a coupler point which will be helped out to find the velocity. So the next step in the acceleration analysis, what you do, that you give again one input, that is angular acceleration of length number 2. So you have to give one angular acceleration. This angular acceleration, let's say if this is alpha 2 in this direction, which is opposite to omega 2, it means that angular velocity is decreasing. And position, and if we have to do the acceleration analysis, we are given with all the variables which are found through position and velocity acceleration. So we have known four lengths, we have theta 3, theta 4, and all these things available. We also have these velocities, and we also have these omegas. So now we are remaining with these things. We need to know what is the angular acceleration of alpha 3, that is unknown. We also don't know what is the angular acceleration of length number 4, that is also unknown. And apart from the angular accelerations, we also have to find the linear accelerations. I also want to emphasize here that length number 1, which is ground length, it is stationary. So its position theta 1 was 0. Its angular velocity, because it is stationary, there is no motion, it will be 0, and its angular acceleration also will be 0. Okay, so based on these assumptions, we'll try to find out these unknowns, and these unknowns will be found in a way that angular accelerations are alpha 3, alpha 4, and linear acceleration at point A will be in such a way that if something is rotating about a pivot point in a circle, it means that its acceleration has two components. One component is along the tangent of this circle, and one uh, vector or portion of the acceleration is towards the center of this uh, circle. So these are the two components, and we will also verify this thing when we will be making the equations. Similarly, for the point B, if it is rotating about 0.04, again it will be a circle, and if it is moving with alpha 4, it has one component of acceleration at tangent to this circle, and another portion of this acceleration which is normal towards the center. And likewise, we have a third acceleration, which is acceleration of B with respect to A. And this acceleration has to come from point B to point A, and that has to move in a way that if the alpha 3 is in this way, this acceleration will be, for momentarily this given position of the 4-bar mechanism, it will be tangent to this circle, and the normal of this uh, circle will be pointed towards the A point. That would be the normal component. So it means that every acceleration has its two components, one is normal and one is tangential, and we will try to verify this when we will do the when we will make the analytical equation for this mechanism. Okay. So quickly, before we do the acceleration analysis, I just quickly go through the position velocity analysis. And for the synthesis and position analysis, we used a vector loop, and the vector loop was made in a way that we made a global coordinate system xy. Position vector r2 was with the origin o2, and then r1 was along this x-axis. R3 was made by taking a local coordinate system at point A, and that local coordinate system was in such a way that it was parallel to the global coordinate system. So if two coordinate systems are parallel, so angle measured by any of the coordinate system is same. So if we measure the angle at this coordinate system, it will be the same like we are measuring it on the global coordinate system. So we will measure the coordinate system here, and we will measure this angle as theta 3 because of the position analysis, and this angle will be found to be theta 4. So these R angles are found based on the vector equation, and vector of equations is made in a way that when you make the vector, the tail of the vector has to be on O2. The tail of the vector is at the origin, and when you make the next vector, you always measure the angle from the tail. So theta 3 has an angle measured from A, the length number 2 has an angle measured from O2, and if you are making this loop angle, we are measuring the angle from O4. So always the angles are measured from the tail, and when we are adding the vectors, you always see that when a vector has a tail attaching to the head of other, they are always added, and if there is tail attaching to a tail or head attaching to a head, these are opposite vectors, so they will be subtracted from one another. So if we follow this method, we will make this equation as r2 r3 minus r4 minus r1, because R2 and R3 are attached with head to tail rule, and R4 and R1 are attached, R3 and R4 are attached to head, and then R4 and R1 are attached to tail to head. So these have one direction of loop, and these have one direction of loop, so these are opposite to each other. We can also write them in terms of the relative position vectors. So if R A is RAO2, that is the position of A with respect to O2, and similarly we can write this vector as RBA, the position of vector of B with respect to A, and similarly we can write this as RB O4, the position vector of B with respect to O4. We can rewrite this loop equation as this one. So I have omitted this O2 from here because normally the origin is not used when you are talking in terms of subscripts, but whatever vector loop equation you use, the end result we will see that it will be same. Okay, so then after the position vector loop equation, you have to substitute the complex number for each position vector. So if a vector has a length given and then it has an angle given, you can use its complex number notation as ej theta or e iota theta, and after that you have to simplify the notation and minimize the use of subscript using the Euler identities. Denote the scalar lengths of four lengths as A, B, C, D. These are the four lengths I already mentioned. So each vector will have this equation collectively in the vector loop. Then we can see that there are four variables in the equation, and these are the four link angles. After that, you can see that link lengths are all constant in this particular linkage because we already have found them from the synthesis, and only thing changing is for every theta 2 there will be two different values of theta 3 and theta 4, and theta 1, as we place the link number 1 horizontal and it is fixed, so it will be 0. Okay, so as we move theta 2, which is the driver link, we get two new values of theta 3 and theta 4. So for every theta 2, there are two different values of theta 3, 4. Okay. Then from this vector equation, we went to the next step, which is the velocity analysis. For velocity analysis, you take the derivative of all these four terms. When you take the derivative, there are two variables in this every term. One is the theta 2, and other is theta. There is only one variable because A, B, C, D are constants, so you only have to take the derivative with respect to these thetas, because when theta will change, you will have the angular velocity. So when you will differentiate, you'll see that when you take the derivative out, this variable remain, this derivative comes into action. So that is nothing but this is equal to omega 2, this is omega to omega 3, and this is equal to omega 4. Okay, so these angular velocities come into action when we differentiate the whole 4-bar mechanism with respect to time. And here this omega 2 will be provided by us, and based on this omega 2 we will calculate the omega 3 and omega 4. Okay, so finally the equation will be this, and here the unknown is omega 3, unknowns are omega 3 and omega 4. Theta 3 will come from the position analysis, theta 4 will come from the position analysis, theta 2 will come from the position analysis, omega 2 will be given by us. So this will complete the velocities, and after the velocity analysis is done, now we are ready to do the acceleration analysis. So for acceleration, you have these three loop equations, and you can see that theta 1 term has been eliminated because that is stationary. Omega 1 was 0, so that term is no more in action. So we have three terms here. If we look the first term and we try to take its derivative with time again, that will give us the acceleration, because first derivative gives you the velocity, the second derivative gives you the acceleration. So here if we see, if we try to take the derivative of this term, j is an operator, its value is equal to under root minus 1, so it won't be differentiated. A is a constant, it is a constant length, so it won't also be differentiated. The things which will be differentiated will be omega 2 and theta 2. So when you will take the derivative of omega 2, it will give you alpha 2. So this derivative will come here. Okay, and if you take the derivative of the second term, it will be the derivative of theta 2. So this omega 2 and this new omega 2 coming from this derivative will come into action here. Okay, so it will make theta omega 2 square and this one will be coming from here, so it will become alpha 2. Similarly, in the second term, when you will take the derivative of this, there are two dependent variables. Iota and b will be eliminated, will not be differentiated. When you will take the derivative of omega 3, it will become alpha 3 based on this relationship. And when you will take the derivative of theta 3, it will come as omega 3 square, and this is coming from this relationship. Similarly, in the third term, when you will take the derivative of omega 4, it will become alpha 4 because of this equation. And when you will take the derivative of theta 4, that will become omega 4, and it will be multiplied by the last omega 4 which is remaining here, and that will become omega 4 square. So all these terms will be disintegrated into two terms. So every one has been divided into two terms. So you can see before there were three terms, now there are six terms. In these six terms, if we try to rearrange them, and we see that whenever you take j square, it is in fact the square of under root minus 1, and it is equal to minus 1. So where you have the square, it makes that it will become minus 1, and those are only j, they are showing that they will remain in the complex form. So you see that this term has come here as minus, and this term has come here. Similarly, I try to clean the uh, space a little bit so that it is clear. Okay, so so this has come here, this has come here. Similarly, this j square after becoming minus 1 has come here, and this term with the alpha has come here. And similarly, this minus j square has become plus 1, but still the bracket is here, so that's why it is coming there, and this plus 1 sign is coming here. So this is basically, you know, that when you take the derivative, this portion which is alpha, and it is coming, the portion which is alpha, which is here, this is basically the tangential component of that acceleration. So this a length is nothing but it is the length of the link number 2, and leg number 2 has is was connected to point A, because you remember that the mechanism was working in a way that this was A, this was B, this was O2, and this was O4, and this was connected with the ground. So the acceleration of A, if it has the tangential component, that is nothing but this component with alpha. So tangential component of AA is coming out to be A alpha 2. So this is the magnitude of this vector. And similarly, the normal component has minus sign with it and omega sign with it. So minus is telling us that it is towards the center of O2, because remember here that whenever you are finding the directions of the vector, the real and imaginary axis work like that. That real axis is along horizontal and imaginary axis is about vertical. Here it is plus j, here it is minus j, here it is plus 1, here it is minus 1. So if something has plus 1 with it, it is real positive. If some term has minus 1 with it, it is real negative. If some term has plus iota, it is imaginary positive, and if it has minus iota with it, it is imaginary negative. So if you clarify here, you can also find out why the directions of accelerations are in this way, because there is no there is one j here, so it's plus j, so it is in this direction, and this is minus 1, so it is this direction. So you see that these two are 90 degree to each other. So that's why when you are building the acceleration of A, so the acceleration of A here is in this direction, and acceleration of E normal is in this direction. So it will also be clear when we will be watching the 4-bar mechanism completely, that these two vectors are at 90 degree to each other, and also the direction of position vector and the direction of acceleration vector are opposite to each other. Similarly, it can be seen in this case. This is the tangential component, this is the normal component, this is the tangential component, this is the normal component. This is for point A with respect to BA, and this is for point B. Okay, so if we try to rewrite this, we see that these six terms are nothing but the three vectors which are for acceleration of 3 points connecting the 4-bar mechanism. So this is the A tangential, this is the A normal, this is the A tangential, this is the A normal, this is the AB tangential, and this is the AB normal. For further explanation of the direction of these vectors, you can go to the lesson where I have explained the uh, real and imaginary axes in more details with respect to position, velocity, and acceleration vectors. Okay, so after we are getting this loop equation, these vectors, if connected together, are showing the same loop which we were talking in the beginning. So this vector and this loop equation are verifying each other. Okay, so we can write them in this way, that AA is nothing but the combination of these two terms. Is similarly AB is nothing but the combination of these two terms, and AB is nothing but combination of these two terms. So these three things are unknown to us, and we will be using these six terms to find them at the end. But at the moment, what we have, we know omega 2, we know theta 2, we know omega 3, we know theta 3, we know omega 4, we know theta 4, we know theta 2, we know theta 3, we know theta 4. These all values are known. Also we know A, B and C. We all know these values because we did our position with synthesis, position and velocity analysis. So what is remaining is alpha 3 and alpha 4. Alpha 2 will be the one which is provided by us. Okay, so at the end when we will be done, and when if we make these vectors and shift them to the point of each specific point on the 4-bar mechanism, so AA will come here, AB will come here, and ABA will also come here. So all these vectors are at their own positions, and they are telling you that how the normal and tangential components are acting. So for the A, position vector was in this direction. I just tell you for 1 point, and its normal component of acceleration is opposite to it, and its tangential component is towards the direction where it has the omega, so alpha. So alpha is clockwise, this tangential acceleration will be in this direction. If assume that omega alpha is here, this will become in this way, because the sense of the linear vector will come from the direction of alpha, but the normal component will always be directed towards the center. Likewise, it is the same for the B point and BA point as well. So this is the vector notation and direction of the accelerations. If we have to actually calculate the alpha 2 and alpha 3, what we have to do, we have these 6 terms and these are in their complex notations. What we can do is that we have to calculate the uh, Euler identities. We will disintegrate it into two components, and we want that alpha 3 should be in terms of 4 link lengths, 3 position lengths, there is no theta 1 because that is 0, 3 angular velocities, and alpha 2 which is given by us here. Similarly, alpha 4 will be a function of 4 link lengths, 3 positions, and 3 angular velocities of the moving lengths, and alpha 2 will be again given by us. And we will be using the Euler identity, which says that every complex identity can be disintegrated into two portions, Cartesian coordinate, Cartesian parts. One is with the cos theta, other is with the sin theta. So for example, if I take this one, this in this A alpha 2 j is equal to R, and if I disintegrate it, it becomes A alpha 2 j cos theta plus j sin theta. And if I open it up, this j will be multiplied by this, so it will become A alpha cos theta, and this j will become j square, and it will become minus 1 sin theta, and this A alpha will be outside. So similarly, we can break all of these. Here there is no j, here there is j. So in every term there is one directed towards the imaginary axis and the other one is directed towards the real axis. But when we will disintegrate, the equations will become more simplified and terms will increase. So if I see how it will be done, so this vector, the first portion, when it is divided, it has been disintegrated into this has been disintegrated into this. So here a omega 2 square is R. The third one has been shown here, so I use a different color here. So this is the two components for this one, and these two are the two components for this one. I again use another color. This one is the two components for this vector, and these two are the two components for this vector. So each vector has two further components. So basically there were 6 terms. So after their equivalent disintegrated terms, they have become 12. Okay, So if I further simplify it and I try to multiply the j inside to see what j square makes the difference, because j square is equal to uh, minus 1 square, so it makes minus 1, so it will just change the sign of the term if it already has a j. So if you see here, this is the j cos theta and this j has become minus, and similarly this minus, and this, there is no j here, so it will remain as it is. So this j when multiplied by this j will become minus sine theta, so you can see it here. Similarly, this j multiplied by this, say, sine theta, is shown here. It is minus 1. And similarly, that's it. So there is no other j term. So all the tangential components, when they will go inside the bracket, they will become j square, and they will be converted into minus 1. So all these terms have been j multiplied inside them. In the next step we will further disintegrate them into their real and imaginary parts. So all those parts which have no j in them, these are the real parts, so these are collected separately, and all those which are having the imaginary portion are here. Okay, so remember always that in the acceleration analysis, imaginary portion will have the cos terms and sine terms combination, and similarly it will goes for the real as well, that there will be combination of cos terms and sine terms. So these are the two equations. Now these two equations can be solved simultaneously, and how we can change them into because these cos and sines are causing confusion, so we can change the knowns into some coefficients, some constants. So for simplification we can say that c sine theta 4, because we know what is c and we know what is sine theta 4, so we collectively call this as a, so this will become a alpha 4, and we can call b sine theta 3 as b, so in this term this will become b alpha 3. And then for c, all the remaining terms in the equation, these all three are known, 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 so we can collectively combine them to make all these 1 2 3 4, we can combine all these three in c, so these have been combined in c. For the d in the next term, we can go for the unknown of uh, c cos alpha 4, this is the unknown, so for this unknown we call it c alpha 4. Okay, that would be not c, it is d, d alpha 4, and then like this. Okay, and then we go for the alpha 3, which is unknown, and we call this as e alpha 3, because e is equal to b cos theta 3. And the rest of the terms, which are these terms, these 1 2 3 and 4, these will be combined to get f. So if we simplify it, these two equations will be taking the form of d a alpha 4 minus db alpha 3 minus dc is equal to 0, and the other term will take the form of d a alpha 4 minus a e alpha 3 plus a f is equal to 0, and we will all get these when we will multiply the first term with d, and then when we will multiply the second terms with a. We are doing this so that we have the same terms of alpha 4, and we can solve them simultaneously. We can eliminate it and we can solve it for a3 alpha 3. So if you solve for alpha 3 in this case, you get that it will automatically become uh, it will automatically become CD. I write DC as CD, and this will go on the other side. AF will go on the other side. It will become minus AF, and on the denominator you can have these two terms that will be uh, A E. This will have plus AE minus BD. Okay, so this is the simplified form of alpha 3. These A, B, C, D, E, F have their values which we just I told you. So this 4-bar mechanism now has all these terms, and now you can calculate for its alpha 3, and similarly you can try to find what is the equation for alpha 4. Okay, so in this way you can calculate the angular acceleration of link number 3 and link number 4. The acceleration of link number 1 is 0 because it is stationary. The acceleration of link number 2, we gave it ourselves. This was given by us. So we have found alpha 3. For alpha 4, you can verify afterwards that this is the equation you found for alpha 4. So if I clarify it here, so you have to verify later that these are the two equations you find for alpha 3, and these are the terms you used for all these constants. This is a to a b c d. Okay, so this needs a lot of care when you're solving it, but ultimately the equation in analytical equation is simplified in a way that you just have to put all these values. Just you have to remain careful when you're calculating these. A computer or a numerical method, not numerical method, a computer based equation like MATLAB or some software can easily solve this without any error. Okay, so when you have calculated the equations for alpha 3 and alpha 4, now your linear equations are remaining, because this is your O2 and O4, and now you calculated your at first you calculated your alpha 2 for link number 2. There was the A point, then there was the B point, then there was the uh, of 4 point. So this is link number 2, which is stationary. You found alpha 2 and you were solving all the system for alpha 3 and alpha 4. When you have calculated them, now you have to come from towards point A, and we already have the equations for point A. Similarly, you have to come for the point B. We already have the point for accelerations for B, and if you want to find the acceleration of B with respect to A, you also have the equation for it, because you have the two terms vector equation for each of them, so you can make use of them. So if we have these four equations which we already built, we can easily find the unknowns of a linear acceleration of A, linear acceleration of B with respect to A, and linear acceleration of B. So this is it. This is how you, using the Euler identities, starting from the vector loop equation, you can find the acceleration analysis. So do comment and give me the feedback for improvement for future. Thank you very much. That's all for today. Before closing and ending, I would again tell you that this today we saw how the acceleration analysis of the mechanism is done using the analytical method, and we use a 4-bar pin jointed mechanism. We gave alpha 2 angular acceleration by our own self, and we solved for alpha 3 and alpha 4, and based on alpha 3 and alpha 4 we were able to find the other remaining accelerations, linear accelerations at point A, which is the joining point of link number 2 and 3, and point B, which is the joining point of link number 3 and 4. And also we were able to find the relative acceleration of B with respect to point A. That's all for today. Thank you very much.